Python strings seem easy until one small mistake silently changes your result or crashes your program. In this video, we will break down 15 real string mistakes, explain why they happen, and fix each one with clear Python examples. We will start with 2 mistakes caused by incorrect assumptions about Python strings. Let us break each example, inspect the error, and then fix it. Suppose we are building a status message containing a user's age. We join the label and age with the plus operator, and now let us run the script. Python stops because these two values have different types. Let us break down the error. The plus operator can join 2 strings, but age is still an integer. Python refuses to guess how that integer should be represented as text. Now we will fix the mistake in 2 ways. We can explicitly convert the age with str or place it inside an f string. Let us run both versions and confirm that they produce the same message. Here's the preferred version for readable messages. F strings keep the text and inserted values together, so the final format is easier to understand. Use them when a message contains one or more dynamic values. Imagine that a generated username must start with a capital letter. We try to replace its first character by index and then run the script. Python raises a type error instead of changing the username. Let us examine why this fails. Python strings are immutable, which means their contents cannot change after creation. Indexing can read a character, but it cannot replace one. Now we will rebuild the username instead of modifying it. We combine the capital A with a slice containing every character after the first one. When we run this version, the corrected username is printed. The reliable pattern is to create and assign a new string whenever text must change. This matches how slicing and all other string transformations work in Python. Keep the original value only when you still need it later. Next, we will look at a boundary error. Fixed indexes are safe only when the input is guaranteed to contain enough characters. Suppose a product code is optional and may contain fewer characters than usual. We try to read the character at index 5 and run the script. The program crashes because that position is missing. Let us break down the boundary. This string has a length of 3, so its positive indexes are 0, 1, and 2. Any larger positive index is outside the string and raises index error. Now we will validate the length before accessing the character. The condition confirms that index 5 exists before Python evaluates it. Running this version prints a useful fallback instead of crashing. The best approach is to check structural assumptions before using a fixed index. Apply this whenever text comes from users, files, or external services and may be incomplete. A fallback message or validation error is safer than an unexpected crash. Now we will test substring searches. A common mistake is treating a returned position as though it were a simple true or false result. Suppose we are checking an email-like value for an @ sign and a hash sign. We place find directly inside each condition and run the script. The output is misleading. The existing character looks missing while the missing character looks present. Let us inspect what find actually returns. The @ sign is at index 0 and 0 is treated as false in a condition. The missing hash sign returns -1, which Python treats as true. Now we will replace the position check with the in operator. It directly answers whether each term exists in the text. When we run the corrected version, both messages are accurate. The clearest existence check is substring in text because it states the intention directly. Use find only when you need the exact position, and compare its result explicitly with -1. This avoids truthiness bugs at both index 0 and the missing value case. Finally, we will transform text into a URL slug. The key detail is that string methods return new values instead of changing the original string. Suppose we are generating a URL slug from a video title. We call replace to swap spaces for hyphens, but we do not store the result. Let us run the script and notice that the printed title still contains spaces. Let us break down the result. Replace does not edit title because strings are immutable. It returns a separate string, and our code ignores that returned value. Now we will assign the returned string to a slug variable. This preserves the original title and gives us the transformed value for the URL. Running the corrected code prints the expected hyphenated slug. The safe pattern is to assign the result of every string method that performs a transformation. Use a new variable when both versions are useful, or reassign the original variable when only the updated text matters. This rule also applies to methods such as lower, upper, and strip. We will start with a subtle transformation bug that can silently damage configuration values. The method name looks appropriate, but its behavior is different from exact prefix removal. Imagine that these values come from an API configuration and we need to remove the token prefix. It is tempting to call strip with that prefix, so let us try it and run the script. The output shows that parts of the actual payload are also removed. Let us break down why this happens. Strip does not search for one exact prefix. It treats every character in token underscore as removable. It keeps deleting matching characters from both ends, which turns value into value and removes neon completely. Now we will fix the bug with remove prefix, which checks for one exact substring at the beginning. If that prefix exists, Python removes it once and leaves the payload untouched. Let us run the corrected version and confirm both values. Now let us show the rule worth remembering. Use remove prefix or remove suffix when the boundary text must match exactly, because these methods preserve the remaining content. Reserve strip for cases such as removing white space or selected punctuation from both ends. Next, we will parse input that contains inconsistent spaces and a tab. A tiny difference in how split is called completely changes the result. Suppose a command was entered with repeated spaces and a tab between two arguments. We will split it using one literal space and then inspect the list. When we run the code, empty strings appear and the tab does not separate the final words. Let us examine the result. The explicit separator matches only the ordinary space character, and every repeated space creates an empty field. The tab is a different character, so staging and force stay in one string. Now we will remove the separator argument and let split handle whitespace automatically. This version groups repeated whitespace and recognizes the tab as a separator. Let us run it and verify that we get exactly 3 fields. Now let us show the safest choice for normal user input. Use split without an argument when any whitespace may separate values, because it handles repeated spaces, tabs, and line breaks. Pass a separator only for structured formats with a specific delimiter, such as a pipe character. Now we will combine several values into one output string. The common mistake is calling join on the collection instead of on the separator. Imagine that we need to combine 3 CSV field names into one line. A beginner may try to ask the list to join its elements using a comma. Let us run that version and see the attribute error. Let us break down the exception. Join is a string method, so Python expects the separator to be the object before the dot. The list is only the iterable that supplies the values. Now we will move the comma before the dot and pass the list into join. This tells Python to place a comma between each pair of values. Let us run the corrected expression and inspect the finished line. Now let us show a simple way to remember the syntax. Read the expression as comma joins parts, which makes the ownership of the method clear. The same pattern works with new lines, slashes, and any other string separator. The final 2 mistakes involve strings that look equal but are compared with the wrong operation. We will cover both object identity and international case-insensitive matching. Suppose a command arrives from input or decoding instead of being written directly in the source. It contains the text run. So we might incorrectly compare it with is. Let us run the code and see that the identity check is false. Let us break down the mismatch is checks whether both variables point to the exact same object in memory, not whether their characters match. String interning can also make identity results appear inconsistent, so this comparison is unreliable for text. Now we will compare the same values with the equality operator. The identity check remains false, but equality checks the characters and correctly reports a match. Let us run both checks side by side. Now let us show the comparison rule to use in real code. Choose equality and inequality operators for string content because they express the actual intent. Use is only when object identity matters, such as checking whether a value is none. Imagine matching a saved username against text entered with different capitalization. We will lowercase Strasse and Strassi before comparing them, which looks like a reasonable solution. Let us run it and see that the comparison still returns false. Let us inspect why the lowercase comparison fails. Lower produces Strass for the first value and Strassi for the second, so the resulting strings are still different. Unicode case-insensitive matching needs a stronger transformation for cases like the German sharp S. Now we will replace lower with casefold on both values. Casefold performs a more aggressive Unicode transformation, so both strings become equivalent for comparison. Let us run the fixed version and confirm the match. Now let us show the better default for user-facing case-insensitive matching. Apply casefold to both values because it handles more Unicode equivalences than lower. If a protocol defines its own normalization rules, follow that specification instead. Next, we will fix two mistakes caused by how Python interprets string literals. These examples cover missing f-string prefixes and backslashes that accidentally become escape sequences. Suppose we are generating an invoice message with a customer name and total. We add expressions inside braces but forget the f prefix before the string. Now we run the script and see that Python prints the braces literally. Let's break down why this happens. Braces only become interpolation expressions inside an f string. In an ordinary string, the name and format specification are just text. Now we fix the mistake by adding an f before the opening quote. Python evaluates both expressions and the .2f specification formats the total with 2 decimal places. Let's run it again and confirm the invoice text. Now let's show the best practice for short local formatting. Use an f string when values belong directly inside a message, and include explicit format specifications for money or measurements. Test the final output because formatting bugs often produce valid but incorrect text. Imagine that we need to represent a Windows path containing new and team folders. In an ordinary string, \n becomes a new line, and \t becomes a tab. Let's print the path and inspect the broken layout. Let's break down the unexpected output. Python processes backslashes before the string is assigned, so the value already contains new lines and a tab. The terminal is displaying those real control characters, not changing the path itself. Now we fix the literal by placing an R before the opening quote, which preserves the backslashes. We also construct a path object so later file system operations use a dedicated path API. Let's run the corrected version and verify both representations. Now let's show the better approach for file system code. Use Pavlov to join, inspect, and open paths instead of manually concatenating separators. Raw strings remain useful when a fixed Windows path must be written directly in source code. Now we move from string literals to text representation. We will compare visually identical Unicode strings and then cross the boundary between binary data and Python text. Suppose duplicate detection compares names entered from different keyboards. These two values both display as an accented E, but one uses a single character and the other uses a combining accent. Let's compare them and print their lengths and code points. Let's break down why equality returns false. The first string contains code point E9, while the second contains a regular E followed by combining code point 301. They render the same glyph, but Python correctly sees different sequences. Now we fix the comparison with Unicode normalization. NFC converts canonically equivalent text into a consistent composed form. Let's normalize both inputs and confirm that equality now succeeds. Now let's show the best practice for user-supplied Unicode text. Pick a normalization form, commonly NFC, and apply it when data enters your system. This keeps comparisons, database keys, and duplicate checks consistent. Imagine that a socket returns a binary response, and we want to append a text label. The response is bytes, but the label is a Python string. Let's run the direct concatenation and inspect the type error. Let's break down the error. A string represents Unicode text, while bytes contains encoded numeric byte values. Python refuses to guess which encoding should connect those two representations. Now we fix the boundary explicitly. We decode the incoming UTF-8 bytes before processing the message as text, then encode the finished message when binary output is required. Let's run it and inspect both representations. Now let's show the safest pattern for files, sockets, and HTTP responses. Decode bytes as soon as they enter the text processing part of the program, and keep using strings internally. Encode only when sending data back to a binary interface. The final mistake appears when string building code grows from a small example into a large report. We will compare repeated concatenation with collecting fragments and joining once. Suppose we are generating a report from thousands of records. This version repeatedly adds each line to one growing immutable string, which can require copying earlier content again and again. Let's build the report and run a benchmark around this approach. Let's break down the performance issue. Python strings are immutable, so expanding a large string may allocate another string and copy existing content. The cost becomes significant when both the number of fragments and the accumulated output are large. Now we fix the builder by collecting each record in a list and joining the fragments once. We benchmark both implementations and verify that they produce exactly the same report. Let's run the comparison and confirm that join is the scalable method here. Now let's show the best practice for large generated output. Collect fragments in a list and call join once, when the final string must exist in memory. For very large exports or logs, stream each fragment directly to the file or destination instead. You now know how to recognize and fix 15 common Python string mistakes. Subscribe and like the video for more practical Python lessons, and tell me in the comments which mistake surprised you or what topic you want to see next.